Hi everyone for coming for the talk. For today we are going to talk about some compiler optimization stuff. And I wanted to talk about one dedicated compiler optimization that is called profile guided optimization. Before the start, I want to share with you some benchmarks that I've achieved. I've achieved great performance results by applying only this optimization without any additional stuff to different kinds of applications and libraries like Rustc, not my work, Vector, that's a log shipping solution, different databases like ClickHouse, PostgreSQL, different libraries, for example, Serdo.json, it's everywhere, XML, RustLab, Tonic, Axum, whatever libraries. I hope you're pretty impressed by these numbers, so we can start. A few words about me, so you can understand my background, what you can expect from me. So I used to be a C++ engineer. I dropped this ubiquitous language several years ago, but as a C++ engineer, I enjoy suffering. And I embrace suffering. So profile guide optimization gave me such an opportunity. Lately I was working as an architect. I was a part of C++ committee. I was working on different stuff, on numerics TS, different numbers, and constant evaluated containers, like a constant evaluation stuff. Besides that, I was hacking for several years LLVM. My area of interest is hardware-independent optimizations. And besides that, I spent the last 2 years with PGO on a daily basis, where I gathered a lot of experience, which I want to share with you. Besides that, I work as a CTO at a top company, nothing interesting to share, like a cybersec company, and that's it. So let's start. Our plan for the talk, a bit of theory about what PGO is, when we'll discuss the current PGO state in the Rust ecosystem. Then we'll discuss briefly practical PGO problems and how they can be mitigated, and a few words about the things beyond PGO. So a bit of theory. Let's start from the basic stuff. There are two major compilation models. Actually, the first one is a ahead-of-time compilation model, where we have our usual CI/CD pipeline, VCS. A compiler takes our source code, generates a binary, and this binary deployed to a target machine. And our way to compile programs is just-in-time compilation model. We are not going to talk about interpretation stuff because it's too inefficient in practice. Just-in-time way is pretty similar, VCS, compiler, source code, but as a result, we have some kind of bytecode, and this bytecode is executed on a target machine, in some virtual machine or whatever you want to call it. We need to understand modern compilers. Modern good compilers perform a lot of optimizations inside them. Inlining, loop roll and rolling, devirtualization, sometime after vectorization that works not so well, link time optimization, and many other things. We are not going to talk a lot about them, but we need to understand that many of these optimizations can benefit a lot by providing runtime information to them. For example, this is the amount of optimizations in LLVM. That's the amount of transform passes. A lot of them. And for example, if you're going to look into the inlining stuff, inlining is one of the most important optimization in the compiler. We see a lot of interesting thresholds inside, like inline threshold, inline hint threshold, and many different things like that. The problem is that these thresholds are not optimal for all programs. And here we have a problem, because in just-in-time way, we have a way to tweak these constants during the application execution, because on target machine we have a compiler or virtual machine. But in the ahead-of-time world, we don't have such a privilege, because no compiler is available on target machine. All the compilation stuff is ended in our CI pipeline. And that's where the profile guide optimization comes in. The idea is really simple. Just let's try to collect runtime statistics on a target machine, as known as a PGO profile, about how our application is executed. pass this information to the compiler and use this PGO profile during the compilation phase. And that's it. Actually, for clarification, PGO, Profile Guide Optimization, has so many names. The first one and the most widely used, Profile Guide Optimization. Feedback-driven optimization is also widely used. It's used specifically for some special kind of Profile Guide Optimization. We'll talk about it a bit later. Profile Direct Optimization, PDF, don't even try to find it, Google. Profile-based optimization, and I even found a PGO, Profile Online Guide Optimization. As far as I understand, there is no difference between PGO and PGO. I will use only PGO. By the way, PGO, according to Google, also is a Pokemon Go. So let's start a simple example about PGO optimization. On the left side, we have a simple function in Rust that compares the input variable with three values, and that's it. And in the middle, we have a resulting assembly that is compiled in the release mode, up level 3. And we have pretty straightforward assembly. One neat detail that the second and the third branches are rearranged for some reason. Clang doesn't do it. Clang is a front end for C++. The reason is because Rustc and Clang generates a bit different LLVM IR for this example. Nothing critical, but that's it. So let's try to apply Profile Guide Optimization. So on the right side, the same release mode up level 3, but Profile Guided Optimized. The training workload, a PGO profile, was a workload where the most frequent input number was 322. And compiler did here some clever decisions. At first, it moved the most frequent branches to the beginning of the function because it will be executed mostly frequently. The second thing, that the return statement also was moved to the beginning of the function because they also executed frequently, so your CPU instruction cache will be happier. And the rest of the function is pretty the same. Let's talk about different PGO kinds. The most basic one is Instrumentation PGO. It's mostly known and widely used PGO in practice. Sampling PGO is the most advanced, a bit more advanced PGO way, and sampling PGO, for some reason, is called feedback-driven optimization. We will talk about the reason later. And actually, there are different combinations and flavors of Profile Guide Optimization. Context-sensitive PGO, context-sensitive sampling PGO, that's no CSS like HTML PGO. There is a temporal PGO. Half an hour ago, I found one more PGO kind, like a lightweight PGO mode. There are a bunch of them, many of them in the state like of RFC in LLVM, and some of them even only are proprietary. So let's start from the most basic one, this Instrumentation PGO. So how does it work? We need to compile your application in the instrumentation mode. Compiler, during the instrumentation phase, will insert additional amount of instructions into your code, like additional counters and so on, and will link additional runtime library that will perform instrumentation phase. Then instrument will perform instrumentation during execution of your instrument application. Then you need to run the instrumented application on some typical workload, collect PGO profiles, and recompile your application once again with these PGO profiles. That's it. Well, another example. A simple function, in the middle, once again, op level 3 assembly for that. And on the right side, op level 3 plus instrumentation phase. Instrumentation mode enabled. The biggest difference is why this additional instruction, increment counter and so on, this is exactly these counters that are inserted by compiler to each function and each branch of your application. And each time then such functions are executed in runtime, these counters are incremented. And then usually at the exit of your program, all these counters from all your program are saved to a memory, to a disk by default. You can tweak this behavior, for example, calling some dedicated runtime compiler intrinsics, for example, to dump all these counters to a memory and then send these counters via HTTP or something like that. It could be important for the cases when you don't have a right access to the disk, and maybe some disk-limited situations like embedded software, for example. And another thing you can find here, LLVM profile raw version. It's a version of LLVM profile file. So PGO profiles, they have some format inside, and also they have versions. And it will create some issues for us in the future. We'll talk about it a bit later. So unfortunately, instrumentation PGO has a lot of caveats. At first, you need to compile your application at least twice. Once for the instrumentation mode, then you need to run during the instrumented binary, and then you need to recompile your application once again. It's pretty tough task, especially if your application is large. For example, imagine Rustc, Chromium browser, ClickHouse database. These are pretty large applications. An instrumented binary is larger because an additional amount of instructions are inserted into your application, and the instrumented binary is slower because the additional amount of instructions are executed in runtime. So let's talk about some numbers. I performed many benchmarks. I just show you here some of them. So here we can compare the release size and the instrumented size sizes of binaries. No worries that in Rust there is only a vector application. The situation is pretty the same for C, C++, and Rust applications, trust me. So here we don't see actually a huge size difference, and since disks are pretty cheap nowadays, so it shouldn't be a problem. However, if you want to use instrumented PGO for the embedded case, please keep it in mind. The much bigger problem is binary slowdown, because actually, in practice, you cannot predict how much of slowdown you will get from the instrumentation phase. It depends on various reasons. For example, if in your application the instrumentation routines will be inserted in really hot and tight loops of your application, you will get a really big slowdown. That's is exactly the case of ClickHouse, and it was confirmed by upstream developers. For other applications, it's pretty different. It depends on the application, it depends on the target workload, and I think that's it. So the only practical way to estimate the actual slowdown, just measure it. Google is the largest PGO user in the world and the largest C++ user in the world. They met all these problems, I think, like 10 or 15 years ago, and they decided to implement another way to use PGO. This way is called sampling PGO. So what is the idea? You need to run your usual application without any instrumentation. Then, instead of collecting runtime information via built-in into your application instrumentation routines, you can try to collect this information via an external profiler, like LionXperf or Intel VTune or even dtrace that we had a talk yesterday about it. Usually, LionXperf is used. Intel VTune can be used, but I didn't try it. dtrace, you will need to implement some additional routines on your own. We'll talk about it later. Then you need to recompile your application once again, this runtime information. And that's it. The rest, the same. Unfortunately, sampling PGO also has caveats. The first caveat is called branch text sampling hardware support. What is it? It's a special hardware feature that allows to your profiler collect much more precise information about how your application is executed with lower overhead. Unfortunately, availability of this feature is strictly dependent on the combination of hardware and operating system. Intel implemented this feature under the name last branch record, and it's available for many years. It also was upstreamed to the Linux kernel many years ago. Sorry, I care only about Linux stuff. I don't know about Windows or whatever you use else. Regarding AMD, this feature is called branch sampling, BRS, and it's available since Zen 3. There is a trap here, Zen 3 for server-oriented CPUs, and since Zen 4 for all CPUs. I found this trap because I have at home a Ryzen 9 from the Zen 3 generation for desktop edition, so I wasn't able to perform these benchmarks. And it was upstreamed to the Linux several years ago. Regarding ARM, there are two features that can be used. The first one is called BRB, Branch Record Buffer Extension. It's available from one of the latest ARM specification. Android ecosystem. This ecosystem, because it's written by Google, it's already optimized by PGO. They use another set of features that are called core side features. Cannot say much. I don't have much knowledge about Android infrastructure. RISC-V, this feature is called Control Transfer Records. Current status work in progress. There is an open ticket. So for other architectures, you need to check on your own, like a PowerPC. As far as I know, it works on it. I've had some conversation with PowerPC maintainers. And another limitation is that this feature doesn't work with virtualization. As far as I know, modern hypervisors don't emulate this feature properly. So if you know something more about this, maybe some good hypervisor try to emulate it properly, please let me know. But according to my experiments, it doesn't work. You need to run in bare metal. And limited tooling support. Why do you need a tooling? So if you want to pass runtime information about how your application was executed, you need to pass it in some format that is understandable to your compiler. Unfortunately, compilers don't care about Linux per format, about the Intel VTune format, and so on. You need some converter. And the first one was implemented by Google. It's called Google AutoFDO. This is exactly the reason why sampling PGO frequently called as a FDO, since this project is called AutoFDO. Unfortunately, Google AutoFDO has many bugs. Build issues with the latest LLVM versions. They don't care much about GCC. In Rust, we also don't care about GCC much. But anyway. And many other things. They don't react in quick way to your reports, because it's Google. There is another tool that is called LLVM ProfGen. So according to the name, it's already in the upstream, so no build issues with LLVM, but there is a limitation that LLVM ProfGen doesn't support sampling PGO profiles without BSS feature. Google AutoFDO doesn't have such a limitation. So let's compare instrumentation and sampling approaches. At first, in general, instrumentation allows to achieve a better performance. Once again, according to Google papers, sampling PGO has, in average case, from 80 to 90% of efficiency compared to instrumentation PGO. Sampling has far less runtime overhead. Slightly 2% of sampling overhead compared to plus infinity of instrumentation. Remember the ClickHouse case. And even this amount of overhead can be tweaked just via the tweaking the frequency of how frequently you sample your application during the training phase. So if you want to get more precise profiles and consequently more efficient PGO optimization, increase frequency. If you want to decrease frequency due to lowering overhead in runtime, for example, production servers, Google invented sampling PGO exactly for the reason that they wanted to collect PGO profiles from production. So you can decrease the frequency, and that's it. And instrumentation has better OS and tooling support. For example, I'm not sure that sampling PGO is available for the Windows platform. Instrumentation PGO is available. So let's talk about PGO state in Rust. PGO support in Rust compilers. Rustc, our favorite compiler, supports both instrumentation and sampling PGO. The same thing for the Ferrocene compiler. Ferrocene is a certified downstream Rustc version. You can be interested in it if you're working in some automotive stuff and something like that. GCC-RS no support, but it can be implemented because GCC infrastructure has some primitives for implementing PGO, because GCC for C and C++ support both instrumentation and sampling stuff. But not the case for GCC-RS, at least for now. MRustC no support, who cares? And other Rust compilers, if any, I don't know, but if any, there is any Rust compiler, I am pretty sure that they don't support PGO. What about support in other languages? C and C++ have the maturest existing PGO implementation in the world, simply because Google invested a lot of money into them. So all modern developments in this area at first implemented for Clang by Google and sometimes by Facebook/Meta developers. Other downstream compilers, let's see, D, Rust, other LLVM-based compilers, almost the same as C++, but without some of the most advanced features like CSS, PGO, and so on. That's a bit most advanced stuff, and at least for the start, you don't need them. Go, since we have a Go Lab conference here, Go added support in the main compiler in the last year. They decided to choose another day, and they implement only sampling PGO without any instrumentation. The reason was simple, because Google uses only sampling PGO in their production, and that's their technology. That's why they implemented only sampling PGO, and that's it. Since the implementation is pretty new, it cannot do much. It can, for now, do PGO optimized inlining, devirtualization, and something else. It's not as mature as C++, but Google knows how to implement PGO, and hopefully it will be implemented, because they care about Go performance as well. C# cannot say much. It's called dynamic PGO. You can read in the Microsoft blog. Pretty good blog, by the way. GraalVM targets GraalVM. It's another ahead of time compiler for the Java and not only Java ecosystem. It also could compile LVM IR. It supports PGO, but unfortunately no evidence about its efficiency in practice beyond synthetic benchmarks, and their documentation is pretty bad. I asked multiple questions in the upstream about their documentation, and at some point they stopped to answer my questions. And regarding other languages and compilers, I'm pretty sure that PGO will not be implemented there, because the proper implementation of PGO, especially if your compiler is not GCC or LVM based, is a pretty tough task. I'm sharing with you the state in other languages, since you will be able to get some insights and share experience with PGO with different ecosystems from different developers from different programming languages. It's a pretty useful feature. So let's start with the basic example, the most basic example, instrumentation PGO in Rustc. Let's compile program, sample program is instrumentation. Run instrumented program is a training workload, whatever you want. Convert the resulting profile to some LLVM stuff, because your application will save to a disk counters in one format, but the compiler requires another format, and you need to convert it. Luckily, there is a pretty handy tool that is called LLVM-PROFData, and you can use it in this way. One detail that you need to use the exact LLVM-PROFData version with the exact version as Rustc, because if Rustc is compiled with one LLVM version and LLVM-PROFData is compiled with another LLVM version, you will highly likely get error like I don't understand this format, and that's it, during the conversion phase. And the last one, compile the program, is the profiling data. That's it. Unfortunately, our programs are not usually small, and we like to use build systems because we are in Rust, not in C++. So Cargo PGO. There is an extension for Cargo that automates a lot of things regarding PGO. This tool was written by Jakub Kobzol-Biranek. This is a person who actually optimized the Rustc with PGO and other stuff. Address, GitHub address, support instrumentation, PGO, and LLVM Bolt. We'll talk about it later. We will have time. And with these tools, the workflow looks something like this. It's pretty simple, and almost all benchmarks for the Rust applications I did in exactly this way. So highly recommend. So let's talk about PGO issues. Oh, in Rustc, pretty of them. So the first one is documentation. Rustc developers don't care much about PGO for users, so the documentation page is pretty small, and if you want to read all interesting information about PGO, there is a link in the Rustc documentation to the Clang documentation. The issue is that they are not fully compatible, and you will need to know a lot about PGO to find the exact, the right pieces of Clang documentation that are applicable to the Rustc. I know them. Many of people, I think, don't. So the documentation can be improved, but as I said, no one cares. Tooling. Unfortunately, Cargo PGO is not ideal. At first, it doesn't support sampling PGO. Secondly, it doesn't support implementing PGO for the no STD cases. So in such cases, requires some additional machinery in a second. And another thing, after PGO migration process, there is a movement about migrating after PGO directly to the LLVM repository. It's a good thing. The bad thing is that they are trying to semi-silently drop the GCC support and move it directly to the GCC repo. And a few weeks ago, a person sent me an email like, hey, look, we tried to drop GCC support, and I'm not sure that GCC, as far as I understand, GCC guys will try to pick up the implementation, but you know, licensing questions like GPL versus MIT, I guess, or Apache, something like that. So questions. Missing most advanced PGO mods. Most of the people don't need them, but anyway. Bugs. The most annoying one that I met multiple times, I guess 10 times in my experience, when you at the same time enable LTO and PGO, during the PGO optimization phase, the compiler will crash on the LLVM side. Jakub Biranek tried to debug it several times, but didn't find the reason. And no one in the upstream cares about it. So that's the current situation. That doesn't mean that every project with LTO plus PGO will crash the compiler. No, not at all. But keep it in mind. No STD support, no STD projects for Rust is no no ECD projects cannot be optimized with PGO by default. However, there is a project that is called Minikov that allows you to optimize it. What is the problem here? During the instrumentation phase, the compiler links to your application an additional library that is called LVM runtime or something like that. And this library doesn't work in no ECD version of your program. If you will add into your application Minikov library and will tweak a bit your application, it will work. I didn't test it in practice because I'm not an embedded developer, something like that. But at least I performed some quick tests on my local machine. It worked fine. And WASM WebAssembly is not supported yet for exactly the same reason, because for the WebAssembly environment, instrumentation runtime is not supported. So if you want to implement WebAssembly and you want to collect PGO profile directly during the WebAssembly execution, you will need to implement the instrumentation runtime on your own. It's possible to do, but you need to do some stuff. So what about current PGO states across Rust applications? Almost no applications support building with PGO in their build scripts for various reasons. We will talk about them later. OS distributions consequently also don't build its software of PGO because maintainers have much different jobs to do, so different priorities and so on. However, some operating systems try to enable PGO in more cases, like a performance-oriented operating system, let's say, like a Gentoo, Clear Linux, or CacheOS. So, as a rule of thumb, if you want to use something in a PGO-optimized way, you need to rebuild it. So, PTR1237 is the main maintainer of CacheOS, and you can see how crazy he is about optimizations. Here he applied all optimizations to the Linux kernel, like LTO, thin version, AutoFDO, like sampling PGO, and Propeller, we'll talk about it later, plus Bolt, and at some point it worked. It's one of the most optimized Linux kernel version nowadays, at least in the open source world. Regarding Propeller, a Bolt, in the end of the talk we'll talk about it. So, what about PGO integration state across Rust applications? Rustc, thanks Capsule. First Syn compiler, no PGO, you will see later the reasons. A bunch of other applications, so situation is pretty sad, no integration. You can see the example of the Vector software. There is a dedicated page about PGO, so they care. The reason that they have a dedicated page about building the application with PGO because I contributed it. And this was the only reason. So, this is the answer from the support of the Firosyn compiler. At first, I tried to convince them to enable PGO to their builds via GitHub. They said that it's not an official sales channel, but I like PGO too much, and I write to the contact at sales something. And I got this answer. You can review quickly about it. Why PGO is not enabled for the Firosyn compiler, especially if the Rustc compiler is optimized with it already. So, the first one, customers don't care about compilation times. Targets that PGO supports in the upstream are not the targets that they currently support. Okay, actually, it's not a good reason because at least instrumentation PGO is target independent, but anyway. It has significant complexity to the build process. Okay, I will agree, especially it's the part of certification. Certification is also always a crazy stuff. Reproducible builds are extremely hard. Yes, I agree, we'll talk about it. Increases build times, yep. There is unknown risk of miscompilation. Interesting reasons, but okay. I don't agree with it. And getting reliable training set for the optimization is somewhat hard. It's not a valid assumption. I am pretty sure that Ferrocene users also usually compiles Rust program as the Rustc users, but okay, I don't agree with the argument. So that's the current state. So let's talk about PGO traps. At first, how should you collect PGO profiles? So there are multiple strategies, but please don't collect PGO profiles from unit tests, because unit tests test your application in many cases. Most of the case, the big part of the cases are corner cases. Corner cases are not your target workload, but anyway. From benchmarks or micro benchmarks, it depends. It depends on how your benchmark suite is representative and similar to your target workload. If they are pretty similar, for example, ClickBench suite for the OLAP databases, it's pretty fine. If you have a bunch of micro benchmarks, it's possibly not the best thing to do. A manually crafted training scenario, that's a good option. Actually, almost all open source projects use this way. For example, if you want to optimize the PGO a compiler, you can write a simple bash script where you compile some sample program, collect PGO profiles, and optimize your compiler. And that's it. This option, by the way, is implemented in LLVM CMake scripts for Clang. And from production, that's a great option, like Google does it. But please be careful, because instrumentation PGO can be actually used in production, but in a very, very careful way. Sampling PGO can be easily used in production. So another question, how long should you collect PGO profiles? So the real question is not how long do you need to collect PGO profiles, but how representative your selected amount of workload will be to your typical workload. For example, if you want to compile a large application, like a compiler Rustc by Rustc, there is no reason to compile the whole Rustc. The workload is pretty the same. It will be enough to compile one of two files, something like that. However, if you have a long process, like with different steps that touches different parts of your code bases, highly likely you will need to run your whole training set, because you want to cover as much parts of your code as possible. So that's it. But anyway, each time when you can try to decide the optimal strategy for PGO profile collection, please perform some benchmarks. So sometimes PGO optimizes some cases and pessimizes others. The reason is because sometimes compiler cannot decide the optimal optimization for all cases. So the mitigation, there are several options for mitigation. At first, try to build per workload applications. So you have two distinct workloads. Just try to collect two distinct PGO profiles and build two distinct PGO optimized versions of your application, and that's it. If it's not possible for various reasons, like a maintenance burden, something like that, you can try to collect multiple PGO profiles, merge them into one, and then you can try to use this one generic PGO profile for your application. It probably will not be the most optimized version for each case, but in general it will be fine. It should be expected, but you will still get some performance boost. Oh, this is a hot topic. PGO optimized build is not reproducible. Actually, that's exact the reason, one of the biggest reasons why PGO is not enabled in operating systems, because reproducibility is a hot topic. There are two major cases here. The first one is a simpler one, PGO optimized build reproducibility. Here, the mitigation is pretty simple. You can try to collect a PGO profile, save to some version control system, and then reuse this PGO profile during each build. And if your build is already reproducible, you will get a reproducible build. The second one is the most complicated. PGO profile reproducibility itself, when we want to gather a PGO profile reproducible in some reproducible way. It could be difficult to guarantee in practice because your application should run in a deterministic way each time. And there is an answer from David Excel from the LVM forum that current implementation can be tweaked with some atomic updates and no value profiling, some neat details. So, but I am not sure, not validated. The problem is, who is Sinlang David Lee? It's the main PGO developer in LLVM. And even the main PGO, one of the main developers don't know the exact answer. So some experiments should be performed in this area. So when you save PGO profiles to some VCS, you will get another problem because your profiles can become outdated because new code is added, existing code is changed, and so on. You can just regenerate PGO profiles, and you can choose different strategies about regenerating, like each build, good options for small programs and small PGO profiles, each release for more serious use cases like enterprise production, and continuous update. It's one of the best ways, but it's really hard to achieve. Google Insight uses such a platform that they implemented a platform based on Google Wide Profiler, which is called GWP, and they continuously sample all the applications, transform them to a PGO profile, integrate into CI systems, and use it in their builds. Unfortunately, no open source solutions yet. There are discussions about implementing on based on Grafana Pyroscope and Elastic Universal Profiling Platform, but nothing to try yet. There are some discussions about implementing as a part of GCP based on Cloud Profiler, and also it can be implemented on some proprietary stuff, like large companies have some proprietary profiling platforms. Can you apply PGO profiles to multilingual apps? Short answer, yes. Yes, actually, but be careful. Very weak tooling support. Imagine the case that you have a Rust application and it has a C++ dependency. And when you apply a cargo PGO, like I shown in previous slides, only the Rust part will be optimized with PGO because now PGO flags are promoted to the C++ part and so on. You will need to pass required compiler switches manually to a C++ via build.rs or environment variable. It's not a funny thing to do in practice, trust me. And even in this case, you can match incompatible PGO profiles format between C++ and Clang, between C++ and Rust part, because Rustc is compiled with one LLVM version, C++ with another one, and it could be a problem. If you compile your C++ part with GCC, it can become a bit bigger problem, but anyway, please be careful. Possible use cases for such usage, like C++ plus Rust applications, and especially like Rust as a core and a wrapper in any slow language like Python libraries and so on. So what about PGO and constant time computations? Because if you apply some additional optimizations, your constant time computing can be affected. So no worries, you are safe with an asterisk. The actual answer, the same guarantees as you had before PGO, because if you implemented some kind of time-based guarantees for your constant time computation, you are pretty safe. If you try to implement something based on compiler optimization stuff, that this optimization will not be performed in this place, you are in danger. So that's it. Can I implement PGO manually in my code? I've asked this question in manually many times. Yes, you can, but please don't do it. So at the previous talk about real-time low latency Rust, Gabriel proposed using manual inlining stuff and hot-cold compiler hints. Trust me, PGO can do it in a much better way than you as a human. And don't spend your time with this, just use PGO if you can. Because maintaining it manually has a lot of disadvantages, like maintenance, more human resources, it's not flexible across workloads. With some hints, you're trying to codify some workload into your application. It could be difficult to implement all PGO applications via compiler hints because they are also tricky. I have a quote from Rainer Gerhardt. It's author of RustLab. It's a log shipping solution. That's a better algo always beats optimizer. So as a context, he is not very interested in PGO. So I hope you remember the low latency Rust talk. So there are a lot of cases when there is no room for algorithmic optimizations. We have cache lines, we have CPUs different, there is room for optimization actually. So don't be like a Rainer in this case. So in some cases, PGO cannot optimize your applications. Congratulations, you use a really good application. So unfortunately, not all software is written in this way. And even if this software can be optimized with PGO for now, maybe later new code will be added, it will be less optimized, so PGO will try to optimize at least this new piece of code. So give it a try in the future. So what about your probable optimization roadmap for your application? Opt level 3, and please enable LTO, please. For like a month, I regularly monitor Reddit, and if I see any new application in Rust, I check if LTO is enabled, and if it isn't, I create an issue, please enable LTO. I am thinking about implementing some automation stuff, but for now I do it manually. Please use fat LTO by default because it's more efficient, thin LTO otherwise if you care about scalability. CodeGen units 1, it's a good option, but up to you. After that, enable PGO instrumentation by default because it's easier, sampling otherwise, and after that, you have something more advanced. Let's talk about it in a very quick way. What is post-link optimization? It's an optimization technique that tries to rearrange your assembly in your binary in the way that it will be located in a CPU instruction cache friendly way. There is a tool, the most widely used tool nowadays is LLVM Bolt, developed by Facebook, already contributed to the LLVM upstream. Less known tools like Google Propeller or Intel Thin Layout Optimizer. The workflow is pretty the same: instrumentation, train, optimization, sampling, and was also supported, at least by LLVM Bolt. And it also has a lot of own issues like limited architecture support, bugs, and so on. I don't have time to discuss it for now. And for now, you can understand this slide. So how many optimizations were enabled by Cache OS maintainer. All of them. And PGO doesn't implement some optimization in PLO and vice versa. So PLO is not a substitution for PGO, it's an addition. And I will show you some benchmarks. So the benchmark is SQLite, it's speed test with the default benchmark. And that's it. So you will see the PGO plus PLO is the most efficient combination of flags. The win, you can say that it's not a big one, but for the SQLite is pretty optimized piece of software. It's a huge win. It's not a noise between measurements. It's a stable, reproducible benchmark. Few words about more advanced things about application-specific operating system. You can try to optimize the whole operating system accordingly to one target workload. For example, Linux kernel for the databases, Linux kernel for gaming. Yesterday we had a talk about schedule in Rust, and they had the same idea. So why not? We can do the same thing, but for the whole operating system. You can try to optimize you can try to make application-specific interpreters like Lua interpreters. I have such benchmarks. Machine learning-based compilers. LLVM already integrated two optimizations based on machine learning based inlining, and machine learning based register allocation. And it showed interesting results, positive results in practice. Actually, we can do practices the same thing, for example, with schedulers. We can try to generate or synthesize a machine learning based scheduler according to some workload. And many academic things like Oculus and Hello, they are not stable, so no worries. So regarding good optimization candidates for PGO, actually any software, it's a lot of branches inside, and almost any software from this conference. Git-trace, it has a language inside, can be optimized, it's CRD-JSON. You've seen the benchmarks. Different parsers, operating systems, SLint tooling can be optimized. Bevy can be optimized with PGO. I have benchmarks for that. Unreal Engine is already optimized with PGO, and many other things. So if you want the documentation, the best link about PGO is my link about PGO, where I try to collect as much as possible materials about PGO, benchmarks, materials, discussions, a lot of questions, and so on. Please go for it. And when you will read, the awesome PGO project, will need to understand the ideas behind this project. The first one, with awesome PGO, I want to introduce more data-driven optimizations for everyone, for many people. And PGO is also a very small step in this direction. Yep, I created some PGO issues for projects and I performed some benchmarks, but not a big price, 500 issues, who cares? And the bigger idea is providing and raising awareness about data-driven optimization. I want to improve the whole performance of the whole industry. It will make actually our life easier, like lower carbon emissions, better UX, lower cost for our CI pipelines, a better battery life for our laptops. So there is an opening keynote that strong software is for a safer future. I wanted to rephrase it, fast software for a better future. Thank you.